Hi, kids. All right, hey, we have a circuit right here. You're going to draw this circuit in your notebook. Okay, that's right. You're going to draw this because you're actually going to take some notes. You're not going to be passive. You're going to be active as you listen to and watch this video. You're going to be taking notes. You're going to pause. You're going to, take some more notes. You're going to pause. You may rewind it because, maybe I'll say some amazing joke or something like that. But you're going to take some notes. So take some notes, get your notebook out, take some notes over this. All right. So here's our situation. So we have a circuit with a couple different batteries in it and a bunch of different resistors. There's two different paths. And let's talk first a little bit about the batteries here. So remember, a battery's job is to supply energy to move the charges that are already in the wires. A really common misconception is that people think, oh, a battery's job is to supply its charge. No, a battery's job is to supply energy to move the charges that are already in the wires. Remember that there's already charges there, and then when you hook up your battery, those charges that are already there are going to start to move according to the voltage and according to the resistance. All right, so let's pretend we have a charge. And excuse me. And it's going to be starting right there. And this charge is going to go around our circuit. Let's pretend it's going to go around this way and get back to there. Now, it could also go the outside way, but we're going to just pretend it's going that way and getting back around there. So we're going to take a little journey with our charge. We're going to pretend our charge is a positive electron, because remember, that current moves in the direction that a positive charge would go. So we're going to pretend it's a positive electron. But if it was an electron, it would be going the other way, which is fine. But it's just electrons are easier to understand or positive charges are easier to understand in terms of what's happening with voltage and stuff like that. So I have a charge right here, and my charge is going to take this journey around. Okay, as it goes around, it's going to be like, all right, so it starts at, let's say it's starting at 0 volts. And then it's going to get energy added to it. How much energy? Well, if you think about our equation, delta U equals Q delta V, that the amount of energy that's going to get added to it is going to be the charge times the change in voltage. Now, if that charge is, if it's the magnitude of 1.6 times 10 to the minus 19th coulombs, which is the charge, an electron is negative that, so that's why I said we have like a positive electron. Then the energy that I gained would be plus, if we're just talking energy, as we're moving around the circuit. So I would add this many electron volts. Okay, remember, if you wanted to take 1.6 times this, then you would get that. So I would be adding that many electron volts. Or if you like, okay, not the greatest eraser, but that's okay. Or if you like, you could say we're adding Q times delta V, that. Okay, then we're at a high voltage, high voltage, high voltage. So now our voltage here is really like this whole thing would be the plus E1 equal potential line, whatever that voltage is. If it was 9 volts, this would be 9 volts. And my charge moves along at this high potential level, and then it gets to this resistor. Well, this resistor is a light bulb, a motor, something that's going to use the energy. So then the electron, as it moves through the resistor, gives some of its energy away to that charge. How much energy does it give away? Well, it would give away Q times the voltage of that. Okay, so whatever the voltage is across there, it would give that. So now it's going to be at a different potential level. What does this potential level be? It would be plus this minus I times R. Okay, or if you like, minus V1. Then it reaches this one. So then it's going to give some more energy away. So it's going to give some more energy away to this charge. Oh, then it gets to this battery. Now this battery, it's going from negative to positive. So it's going to boost its energy. So then it's going to add Q times that many volts. Then it's going to get over here, and it's going to be like, I got another resistor, okay? And it's going to lose that much, which would be Q times V5. And then it would get back to here, and it would then lose that much as well. And it would be back at its starting point, okay? So again, this would be an equipotential line. This would be another one. This would be another one. This would be another one. This would be another one here, okay? And then that would be a different equipotential line. Now, I end up with this. And if you notice, okay, that I could make all the Q's go away, but we're going to leave them there. And that's really my loop rule equation. So hopefully that makes sense, okay? I could go on the outside path too if I wanted. But that's a single charge that's moving. If I wanted to know what is the charge per time, or like what is the energy per time? So if I wanted to do energy per time, well, energy per time is defined as power. Remember, power is the rate energy is converted. So if I take my equation here and I just go per time, per time, per time, per time, per time, per time, well, what I'm really doing is I have Q over T. What is Q over T? Q over T is current. So I'm going to end up with that. I'm going to end up with I times V is going to be equal to your power. And lo and behold, that is what it equals. So power equals I times V. But I want to make sure it makes sense to you in terms of a single charge going around, what is happening in terms of energy, in terms of voltage. And then if we're talking about lots of charges moving, we would be talking about the rate that energy is being used, which would be the power. Remember, power has the units. If you look at units, I have coulombs per second. That would be I. And then I have V is a joule per coulomb, which lo and behold, why did I do that? Lo and behold, let's try that again. Okay, my coulombs go away, and I end up with a joule per second. And I don't know if you remember what a joule per second is. Yes, it is a watt. What? It's a watt! So like I said, if you want to rewind and listen to that amazing, joke, what is that? It's a watt, okay? But yeah, so it would be a watt. If you have, for example, and this is the same thing, if you have a 60-watt light bulb, what? A 60-watt light bulb. What that is saying is it's converting 60 joules of electrical energy to light and probably heat, because it's probably getting hot, to light energy every single second. Okay? All right. Hopefully you took some notes. Hopefully that makes sense. Essentially, the big takeaway is power, and just remember power is also defined as the change in energy per time. Okay? But that's how you find power in a circuit. Bye, kids.